Section 5.8 is almost an extension of what we were doing in 5.7. Last thing we were doing in 5.7 was derivatives of trig functions. This one's going to be, inverse trig functions. This one's going to be the integration of the inverse trig functions. So to start with, we have some forms that we're, again, not going to ask you to memorize, and they're going to kind of look like some of the things we saw last time in reverse. These involve inverse trig functions. Notice we're not finding the antiderivative of arcsine, arctangent, arcsecant, and so forth. But these are the ones that come about as we take a look at certain rational looking functions, right? They look like, or maybe irrationals in the denominator. So the first one is 1 over the square root of a squared minus x squared dx. This is the arcsine of x over a, obviously plus c. When we have 1 over a squared plus x squared, we get 1 over a times the arctangent of x over a plus c. And we have the antiderivative of 1 over x square root of x squared minus a squared dx. We have 1 over a arcsecant of the absolute value of x over a plus c. And what we're going to be doing here is finding some integrals. And of course, we're going to see some u substitution. And we're going to see another algebra thing that you may or may not remember coming up as we work through this. So we're going to start with this integral. So this one says we're going to find the integral of 1 over 4 plus x minus 3 squared dx. So if you take a look at the three forms that we're given, this most closely resembles number 2. There's no square root. So it's going to be an arctangent kind of form, but it's not exactly in the form that's most helpful for us. I want it to look like some things that are squared. So we'll start out by rewriting the 4 at the beginning as 2 squared. And right here, I really want this to be a single thing squared. So we're going to do this as u substitution. It's not a very exciting u substitution, but it's okay. U is x minus 3 dx. And then the du is going to just be, that's a minus, just be 1 dx. Okay? So we can replace the x minus 3 squared with u squared, the dx with du. And we can use the arctangent piece that we saw on the previous slide. Now, the a value is this number right here that has been squared. So my a, we'll note over here to the side, is actually 2. It's the first piece that's being squared. So in the arctangent function's derivative form over here, right, the antiderivative piece, it says we're going to do 1 over a. So this is going to be 1 over 2 times the arctangent of the variable, which our variable right now is u, over the a value, which is 2 plus c. Of course, we can't end there. We need this arctangent u to be an arctangent x. So we have arctangent of, and then the u is x minus 3, still over the 2, and plus c. Okay, so again, the u substitution, they're not very exciting. We're going to do one on the next one. It's going to be a little bit more interesting. So on this one, you do notice that there is a square root in the denominator, which means it's going to match one of the other two forms that we have. In particular, it's going to match form number 1 because it doesn't have anything multiplied outside of the square root of x squared minus a squared, right? So we need to figure out several things. First, we need to figure out what u would be. And then we also need to figure out what a would be. So those are identified from the denominator right here. So my a would actually be 5 because the 5 squared would be 25. And my u would be the tangent of x. If I do that, dx, the derivative of tangent x is secant squared of x dx. Oh, sorry, this dx was in the wrong spot. Got off my notes. That's where my dx was meant to go. Apologize about that. Secant squared of x dx, which is in our problem, right? So the secant squared of x dx is over here, right here at the end. So we'll be able to do that replacement as well. So doing a few replacements, we have 1 dx at the end. Sorry, secant squared dx at the end becoming 1 du at the end. There we go. We have our 25 being rewritten as 5 squared. And our tangent squared is now u squared. And now it actually has the form that I can use this arc sine function at the beginning and write the closed form. So this says it's going to be the arc sine of the variable over the a. So my arc sine, my variable right now is u, over the a, which is the first piece squared, which is 5, plus c. But of course the problem didn't start out with u, so it won't end with u. We will change the u back into what u is equal to, which is the tangent of x, and then that's over 5 plus c. Next one. Feels a lot like the previous one, except now we actually have limits of integration on the top and the bottom, right? So it's going to have that component at the end. For starters, notice there's no square root in the denominator, right? So this is going to be most closely matching number 2 because I don't have a square root in the denominator. So we're going to let the a value be the value at the beginning. It's 1, right? Because 1 squared is 1. And the u value is the number that's squared at the end. Now, it may be hard to sort of see this. This is something squared, but it is. This is e to the x squared, right? That's the same thing as e to the 2x. That's e to the x squared. So the u is e to the x over here. Du, right, the derivative of e to the x, he's our best friend, is e to the x dx. And we see the e to the x dx showing up at the top and the side. So that's there. So I'm going to leave my limits of integration off as I rewrite this in terms of u, the derivative, and rewrite this in terms of u and then take the antiderivative. So this is going to be replaced by the 1 on the top and the du at the back. I have 1 squared, so I'm going to write it as 1 squared, even though it feels a little funny. And then instead of e to the x squared, I now have u squared. The antiderivative form on the previous slide said that this is 1 over the a value, which is 1, arc tangent of u over a, which is 1. And then, so I won't write the 1 over 1 at the beginning anymore. This is the arc tangent, and the u is e to the x. So e to the x over 1 is e to the x. And now it's back in terms of x. I can put back in my limits of integration, natural log of 5 and 0. Okay, let me shrink this up just a little bit so it's more space to work. So we're going to do arc tangent of e, and then the x is now natural log of 5, minus the arc tangent of e to the 0. So a few of these have values we know. Right, so the e and the natural log, those cancel, leaving me with arc tangent of 5. Over here, the e to the 0 is actually equal to 1, so this is the arc tangent of 1. Now these aren't logs, so I can't like combine them into like, this is the arc tangent of 5 over 1. It's not like that. That'd be nice, but it doesn't work. However, the arc tangent of 1 is something we know. So we'll think back to our unit circle. Some of you like that one better than the others. That's okay. The arc tangent would be a tangent value that is 1. Right, we want a tangent value that's 1. In particular, that must be that's in quadrant 1, because tangent is in 1 and 4. So it has to be in quadrant 1. And for my arc tangent to be the same, the x value and the y value have to match. And they match right here at this 45-degree angle or pi over 4 angle. So this is the arc tangent of 5 minus pi over 4. All right, last one, and it gives us some directions on how we're going to process through this. It says complete the square if necessary, right? It will be necessary. That's why I chose this particular problem. So let's take a look. If you look at that denominator, I do have a square root in it. So it's going to match either 1 or 3. It matches number 1 again, so I realize as I'm doing this, I didn't actually have an example of number 3. That's okay. You'll see examples of number 3 in your homeworks as well. But this is a number 1 problem because there's no variable multiplied on the outside. It's just a square root singly of some things in the denominator. The problem is that this does not seem to have that form of a piece that's squared minus another piece that's squared, right? It doesn't have that form. And so we need to get it to have that form, and we can do that by completing the square. So let me remind you about some completing the square stuff. because you probably haven't seen it in a while. We need to have the denominator look like two pieces that are being squared. So the key to completing the square is to take the middle value, divide it by 2, so 2, times any variable or any constant that's multiplied by the x squared term. So b divided by 2a, we will square that. So in our problem, our b value, let me put this over here just a second. Our b value right here is 4. So we have 4 divided by 2 times our a value. So our a value is 1. I mean, -1 if you wish, that's fine, -1. Because I'm squaring it, it doesn't really matter, but we're squaring that. So I have 4 over 2, that'd be 2. 2 squared is 4. All right, so I reduced inside, got number 2, I squared it, I got the number 4. This number is the number I'm going to need to add to complete the square. So here's what that looks like. I take the negative x, so this is the part that's under the radical. Let me identify that. Under the radical. So I take the value that's underneath the radical, which is right now negative x squared plus 4x, and I add 4 to it. But this adding 4 business means I'm also going to need to subtract a 4. Right? I can't just go adding and subtracting quantities. Like, that doesn't work. Now, this is a little bit trickier than the way that I've written it down. It might not have written it down in the best way possible. But in fact, let me take a step back and do that. Let's do this before we do it. Let me take this off. Go back to where we had original piece. I'd like to just take that negative out of this. So it would be more helpful to me if we rewrite this as a negative on the outside and the negative 4x here. Let's do that. It's a better place to start. So all I've done right now is factor out the negative. Notice I've left a space beside the negative 4x. That's actually where I want my plus 4 to go. I always need an addition piece to complete the square. And then that value negative or value 4 is actually really a negative 4 because this 4 is multiplied by this negative on the outside. So right now I've added a negative 4 to my problem. So to compensate, I need to add a positive 4 as well. So there's a positive 4 on the outside. And then we're going to factor what's underneath this. So how do we do that? Well, it's always a perfect square factoring. That's the whole point of why we did it. It takes the first piece, the square root of it, so that's x. It takes the square root of the last piece, that's a 2. And it takes the sign from the middle, it's a negative. So this will factor as x minus 2 quantity squared. And the number at the end is a 4. Now, the form, if you'll notice over here for this, however, has the constant being squared at the beginning and the variable component at the end on number 1, right? Constant squared at the beginning, variable component at the end. So I'm going to rewrite this piece. There it is. That's underneath the radical. With the constant at the beginning, that's my 4. And the variable piece at the end, that's my minus x squared, or x minus 2 squared. And instead of writing 4 at the beginning, it will probably be useful if I write it as 2 squared. Okay, so what this does up here is it rewrites everything that's underneath the denominator as 2 squared minus x minus 2 squared. That's what we have. Dx at the end. Okay, at this point, it looks a lot like the other things that we've already done. I can identify that my a value is 2, and the u value for my u substitution will be x minus 2. But the derivative of that, not very exciting, is just 1 dx. So as we work on taking this and shifting it into u's, we'll need to keep those things in mind. I still have a 2 on the top, but, and I have the 2 squared on bottom, but now I have the minus u squared on bottom, du. Now an antiderivative, the 2 on the top just comes along for the ride. I'll write it out in front. And then this is, according to the antiderivative rules that we saw over here, number 1 is arc sine of x over a. So this is arc sine of my variable, which is my variable is u, over my a, which is 2, and then plus my c. Okay, we're just about done. Our u value, arc sine, my u value is actually x minus 2 over the 2 that's already there, and then plus c. Do not be tempted to think that somehow you can simplify this 2 and this 2. You can't. One of them is inside of an arc sine function, and the other one is on the outside of it, so they cannot be combined. This is, the final answer for our problem.